in presenting tonight's speaker, Josh Lilienthal. Josh, all you.
Before we get started, I'd like to thank Seismic for sponsoring this Tech Talk. Today, I want to take some time to discuss data modeling. Now, your first instinct on hearing that might be to tune out, but I think in a few minutes I can prove to you that data modeling is essential learning for anybody who intends to work with databases and pretty darn interesting to boot. So what is data modeling? Put simply, this is just the process of creating a visual representation of the data a business or organization collects and how it flows and relates to the other data. Once applied, a data model will also define the shape of your database. And good or poor models can have huge effects on the speed, storage cost, and integrity of your data. Data modeling can seem broad and overwhelming at first, but by applying a few essential concepts, we can break these abstract concepts down into a very logical approach. So before we dig into the complex stuff, let's take a look at a real-world example of good data modeling in practice. Natural disasters have a huge effect on commerce in an affected region, and just like it's important for individuals to prepare for a storm, it's also important for businesses to prepare for a storm. In the early 2000s, Walmart conducted extensive research into the effect hurricanes had on their customers' consuming habits. You could probably hazard a guess at most of the findings, that people were more likely to stock up on essentials like flashlights, batteries, water, and the like. What I bet you didn't guess was that people were also 7 times as likely to buy one other item: strawberry Pop-Tarts. Based on this data, Walmart was able to stock up on the prerequisite items before storms going forward and help fill the demand not just for essentials and the obvious things, but for comfort food as well. Good data modeling was able to give us some information that no amount of pure instinct or intuition could have. So now let's talk about bad data modeling. If we're not thoughtful and proactive in our data modeling, things can get furry and bad practices can come back to bite us. First, let's look at a few. Sometimes business practices can affect both the shape and effectiveness of our data. Well, what's the problem with that? Unlike our data model, which should be largely cemented once we're up and running, business practices are going to change and evolve over time. Say you've got a table displaying the profit made on items sold in our store. This looks fine enough at first glance, but what if the business introduces a discount program and we've got data in other tables that's dependent on the profit column here? The data model wasn't built with a discount program considered, so the profit is no longer going to be accurate. Another problem area is going to be defining our entities, which are the data collected. Say our business offers services in addition to products. It might make perfect sense to us to separate these areas of interest, but on closer examination, the tables are virtually identical. We're collecting the same information for products as we are for services. This is going to lead to issues down the line. Let's say I bump prices up 20% across the board because the industry is just so hot right now. Oops, see the problem? Retail and profit updated their price values correctly. Price per hour did not. Now our profit numbers are incorrect on all our services, and that's going to be a huge headache for us to fix. Had we not decoupled our item and service pricing, they would have all updated together, but our unnecessary separation of entities caused an anomaly. Referential integrity is going to be another consideration. Here we've got a table of one table of users on a website and another table containing users who subscribe to our newsletter. Our subscriber ID should match to a user ID value so we know which user is subscribed. Whoops, looks like we had an error when we entered the subscriber IDs. ID 101 doesn't exist in our user table. We didn't validate our relationship to an existing user ID, so now we're referencing a value that doesn't exist. That's going to cause problems. These are just a few basic examples of why we need to approach our data model thoughtfully and with caution, especially as we move up to scale. So now let's talk about how we can structure our database as a whole using either relational, which is SQL databases, or non-relational, which is NoSQL databases. It's important to understand a few of the key differences between these strategies if you're going to create a competent data model. SQL databases are organized into tables, similar to something you might see with Excel or Google Sheets. They're built up of columns, which describe a single type of data, and rows, which describe specific records. SQL DBs are carefully structured, and they use a schema to define the tables, columns, and relationships of the data. The relationships are declared using primary and foreign keys, which we'll go into more depth on later. NoSQL, on the other hand, is much more free-flowing. In these databases, you're going to see data organized into objects that closely resemble JSON. They can include nested data like arrays and other objects, contrary to SQL, where that's not really done. NoSQL is much less structured and doesn't require a schema, although you can use one if you desire. Overall, these databases are much more flexible than SQL, but also a lot less predictable. You may opt for a non-relational database if you anticipate frequent and less predictable changes in your data structure, but because of that unpredictability, this presentation is going to largely focus on SQL databases as they can be more semantically modeled. When crafted thoughtfully, a relational data model can serve an organization in perpetuity and scale up with very little friction. It just requires some careful planning, which brings me to my next topic. To be able to shape your data model, another essential topic to understand is the way different pieces of data relate to one another, known as data relationships. So when we describe the relationship between specific columns in a table, we often refer to the number of a value in one table compared to a corresponding value in another table. That's going to be called data cardinality. There's a few different types of these data relationships you're going to need to understand, starting with one-to-one relationships. This describes a single record from one table which corresponds to exactly one other entity in another table. So for instance, one individual has a social media profile that they've created just for them. We may detail that individual's name, age, and hometown in one table, and the details of their profile, like URL, about me, profile picture, things like that, in another table. But that profile belongs to one person, and that person may only create one profile. The next relationship is one to many, or many to one. This term describes a relationship in which a single record in one table may be referenced many times in another table. For example, a single shopper has multiple transactions in a day, so one person is referenced multiple times in the transaction table. The last cardinality relationship is many to many. In this data relationship, records in both tables may appear many times in each other's tables. So we have a table of items sold by a business and tables showing items purchased by each customer. One customer might purchase many different items, and the same item might be purchased by many different customers. A broader data relationship that's important to understand is the relationship between primary and foreign keys, which we'll talk about in just a moment. First, let me introduce our next topic, normalization. Let's look at a normalized data model. For this example, let's use the frontman of critical darling and award-winning rock band Limp Bizkit. Normalization is a classification associated with data that is formatted to reduce repetition or redundancy and increase data integrity. As you can see, the data is laid out quite readably for human eyes, and it's neatly organized into consistent tables. Before we dive in, let's review a couple of important data modeling vocabulary terms that are going to be relevant here. These terms play heavily into the concept of normalization, so we'd better be familiar with them. Primary keys are the most important column or columns in a data table. They're going to act as unique identifiers of the content in each row of that table. Foreign keys are simply primary keys that are used in another table to act as a reference back to the original table. Let me show you what that looks like. Back to our normalized data example. Each table bears a relationship with at least one other table. In this case, the relationships are all many to one. Makes it easier to visualize. Many people are going to work for one business. Many businesses are owned by one organization, and many organizations are part of one industry. Our primary keys are unique values used to identify specific records, and they can be used as a foreign key on another table to forge a data relationship between tables. Our business ID field, which is a foreign key in our person table, corresponds to the ID field, which is a primary key in our business table, telling us that Fred Durst works for the business Limp Bizkit, which is part of the organization Cash Money, which is part of the music industry. Put simply, the primary key in one table connects to the same value, which is used as a foreign key in another table. There's two more terms I want to go over briefly. The first is going to be data integrity. Right, so data integrity is a concept and process that ensures accuracy, completeness, consistency, and validity of an organization's data. Normal form is the measurement of integrity of our data through the process of normalization. Normal form's characterized by its classifications known as NF. 1NF, 2NF, 3NF, and so forth allow us to assess the risk of data contamination, which is a breach of our data integrity in our database. The higher the number, the safer and more normalized our data is. Let's return to our example data model. We're going to talk a bit more about those normal form classifications from the last slide. This model is heavily normalized. So to achieve 1NF normalization, which is the bare minimum to be considered normalized data, a few things are going to need to be true about our data. Firstly, a single cell should only contain one piece of data. In our person table, if I were to put name and role in the same cell, this would be a violation of 1NF standards. These data are not closely related enough to be considered one piece, and either role or name could potentially change at some point, which is going to pollute the other piece of data. It's also going to make retrieval of that data a lot more complex for no reason. Secondly, every table is going to need to have a primary key. Your database platform should prevent duplicate primary keys from being created in the same table, which can help with data integrity, but you must have one primary key in each table. In this example, that would be the ID columns of each table. Another important rule is that the attribute domain cannot change inside a column. Now, that's just a fancy way of saying that we can't mix up our data types. So if I've got a column of heights, I shouldn't spell out 6 feet in one record and write the numeral representation in another. Another rule is that a record is not going to have repeating groups or values containing multiple pieces of information, even if they're closely related. So for instance, if I made a table for my wardrobe, I wouldn't store an array of my clothes on a single record. That would make retrieval and use of any piece of data in the array more complex and error prone. Each row also should not have repeating groups. So in my wardrobe table, I wouldn't title a column shirt 1, shirt 2, shirt 3, etc., because I might not know exactly how many shirts I have. That number can change at any time. So setting a static limit on the amount of data I can store by using multiple columns for the same kind of item is going to just add unnecessary complexity, which will lead to errors and anomalies. It would probably be better to just have shirt be a column instead, so we can add as many rows as we need. In 1NF, the rows have to be in arbitrary order. That is to say, no meaning should be assigned to the order of rows within a column. For instance, I wouldn't want to create a table that rates Limp Bizkit's greatest hits using only the row number to mark their ranking. That data would be assigned to its own column with some sort of value attached so we can actually retrieve and use that data in some way. That's going to be the last requirement for the bare minimum normalization class of 1NF. These are the standards that together normalize your data to 1NF or first normal form. So let's move on to 2NF. Firstly, every normal form assumes you meet the standards for the forms that came before, so the first rule of 2NF is that you must be normalized to 1NF. The next rule is that every non-key attribute, what you see highlighted here, is going to be, which is every property besides the primary key, must be dependent on that primary key. So notice how in this example, every column is directly dependent on the first. Again, the primary key in this case is the ID of this person. The name belongs to this person. The role is this person's role. This person's hands are up, and this person works for the business ID at the bottom, which is the foreign key for the business table. So although every table must have a single primary key, a primary key can actually be composed of more than one column. But to be normalized to 2NF, every non-key attribute must be dependent on the entire primary key. So if we do use multiple columns as the primary key, we have to pay really close attention to our dependencies. Let's say for some reason we decide to use both name and album as our primary key in our greatest hits example from earlier. That leaves rank as our only, non-key attribute in the table. We know rank is dependent on name because name identifies the song being ranked. However, rank is not dependent on album because we're ranking songs here and not albums. These two columns have no direct relationship whatsoever with one another, and so rank cannot be dependent on album in 2NF. With just name as our primary key, let's go ahead and re-examine things here. Album is dependent on name because the song tells us what album is being identified. Rank is dependent on name because the song is what we're ranking. So this is going to properly normalize our data to 2NF. Nice. With these enhanced standards, when put together with first normal form, you're going to be normalized to 2NF or second normal form. That's the last normal form I'll detail here today, but it's worth noting that there's many more classifications of normalization going all the way up to 6NF. If you're interested in normalizing your data to the fullest extent, I'd recommend looking further into the remaining classifications. For contrast, let's briefly discuss the alternative to normalization, denormalization. So if performance is an essential consideration to your data needs, you may want to consider some level of denormalization in your data. As we learned before, normalization prioritizes integrity of data and readability to keep our data clean and accurate. On the left, we have a table about the roles portrayed by actors in the movie Face Off, starring Nick Cage and John Travolta. On the right, we have a separate table with details about the stars, and below that, another table with details about the roles those actors played. This is the same data in denormalized form. As you can see, we combined the previous 3 tables into one large table about the stars of the film, the roles they portrayed, all in one table. Now we can get the character's name and age in the same table as the actor's name and age. This reduces the difficulty of formulating queries and the need to make complex joins to access a piece of data. As a result, making calls to our database will be faster and have better performance. Sounds good, right? Wrong. Well, let's say this face-off table is part of a larger data model containing many different films. We'll look at another table for the Wicker Man underneath the first. As you can see with denormalized data, we can fit a lot more information inside a table. But there's a problem. Do you see it? Nick Cage's age is shown as 59 in the Wicker Man table and 60 in the Face Off table. I don't know, maybe we made the Wicker Man table before the Face Off table and never updated the age for Wicker Man after Nick Cage had a birthday. I don't know. The point is, because this piece of data, in this case, Cage's age is duplicated, it doesn't update in all locations at once. This is called an update anomaly. That's when an unnecessary redundancy causes your data to lose its synchronization, and it's one of the potential downsides to denormalization. So let's review the pros and cons, right? On the one hand, when we use denormalized data, we have no need for complex joins, and we'll have simpler queries overall. Our model will also be more faster and more performant than a normalized data. Speed means reduced server load, which could save you money. On the other hand, unless we plan our model with extraordinary attention to detail, we will also see a reduction in our data integrity, which can lead to anomalies like the update anomaly we saw before. We'll also have increased redundancy in our model. This is less readable to humans and can have unforeseen side effects. Increased redundancy also comes with higher storage costs, which might offset any monetary savings that you might get from reducing our compute load. In the end, the decision comes down to the priorities and needs of the organization, but some level of normalization is arguably going to be better in most use cases. That wraps up the major topics of discussion for this presentation today. So let's take a review of what we've learned. Good data modeling can provide many benefits to an organization, both obvious and more subtle. We can store and retrieve our data quickly, reliably, and accurately with a low performance cost, and we may even discover things we never could have intuited without hard data. Bad data modeling is worth taking the time to understand and avoid, as it can cause huge headaches down the line. It's much more time consuming to fix a poor data model after you've collected 6 months of bad data that now needs to be updated than it is to do things right in the beginning. Data relationships tell us how our data flows and interacts. Cardinality describes the number of relationships in one table that relate to the number in another. One to many to one, and many to many. Primary and foreign keys forge the data relationships between tables through unique values that define every row in a database. SQL databases are highly structured and rigid, but can be complex to query. NoSQL databases are going to be more flexible, easier to query, but a lot more prone to improper data modeling. Normalization is the process of making our data resistant to anomalies through an escalating series of classifications called normal forms. Normalization is going to emphasize human readability and data integrity over performance. Denormalization is the process of creating redundancies in our database to increase our performance and reduce the complexity of our joins and queries. So denormalization emphasizes fast reads and writes over ease of use of human readability and data integrity. This is my works cited page. Here's my contacts and my links. And thank you so much again to Seismic for sponsoring this Tech Talk. Good night, everybody.
Thank you, Josh, for that delight-filled tech talk. Unfortunately, we don't have time for questions, but Joshua, thank you again. Much appreciated. Bye, y'all.